Now, when we talk about the structure of an atom, when I was introducing the topic to you, I explained how in the structure of an atom, a proton or a neutron is not the smallest particle, right? That a proton and a neutron can be broken down further. Before we can actually talk about what happens when we break down protons and neutrons, what do we get? What is particle physics? We actually have to go over atom itself. So let's first go over atom. Okay. When we talk about atoms, so there have been numerous theories over the years about the structure of atom. Over the years, you will find so many theories about how an atom is actually going to be looking like, right? Now, when you go ahead and talk about it, so uh, when you go ahead and talk about it, so we can take this back to the early 19th century. 19th century would be your 1800s. So in 1800s, that the idea came of theory around 1800s, early 1800s. They came up with a theory which they call the plum pudding model. It was called the plum pudding model. What actually was the theory? The theory was quite simple. So the scientists actually discovered, right, that the scientist actually discovered that there are electrons. Okay. And he discovered that the electrons could be removed from the atom. And when the electrons could be removed from the atom, a positive charge is left behind. Right? So at that point, he came up with this particular model that, you are, when you go ahead and talk about it, that that basically an atom is a mixture of this was around 19. That atom is a mixture of positive and negative charge. Okay. Around 1800s, around 1800s, they actually used to believe that the atom was simply a hard solid sphere. Around 1800, they simply used to believe that, it's just a sphere. That's all it is, right? Now, it was around 1900s that another scientist, of course, discovered that the electrons could be removed. And when the electrons were removed, you would end up getting a positive charge. So he said, okay, that means an atom is a sea of positive and negative charges. That's what he said. Fine. Now, after that, further discovery, and at that time, this theory matched all the information, all the evidence at that time, whatever evidence they had. This theory made sense according to that evidence. Now, it was around 1911 that a scientist whose name is Rutherford, right? He was the one who came up with the model where he said that it actually has a tiny charged nucleus, right? Carrying most of the mass, surrounded by electrons. He was the one who came up with the theory basic model that we follow these days, right? And with most of the atom being empty in space. All right. So it was around 1911 that we came up with this idea. Then later on, another scientist, his name was Bohr. You don't have to remember the name of the scientist. Bohr was the one who actually figured out that, your electrons are going to have shells. Your electrons are going to be in their fixed orbits. That electrons are going to be in fixed energy levels, because that's what shells are. Shells are energy levels, right? So they're going to have fixed orbits, or they're going to have fixed energy levels, right? And the electrons can move, or they can jump from one orbit to another by gain or loss of energy. So they can gain energy or they can lose energy, and they can go from a lower shell to a higher shell, or a higher shell to a lower shell, right? And apart from these jumps, the electrons are in fixed orbit. Now, this is the model that we actually follow these days, right? This is the model that we're actually following these days. It's not perfect. It has a few weaknesses, but this is the most accurate, currently one of the most accurate uh, orbits models that we have. Now, the question comes, how did we figure out this? How did we figure out all of this evidence? How did we figure out all this information? How did we figure out the structure of an atom? So, the structure of an atom was one of the major experiments. This is the result that we're seeing, Ridena, over like centuries of experiments, right? But the main experiment that you have to know from your syllabus, the main experiment that actually gave us all the information that we are currently talking about, that experiment is basically known as the alpha scattering experiment. And that's what we're going to go ahead and take a look at. We'll be taking a look at alpha scattering experiment. And this was the one that actually helped us come up with the model, right? Now, when we go ahead and talk about it, what are we going to be seeing? So the alpha experiment experiment was done something like this. So when you go ahead and you talk about it, they had a chamber, right? This is, for example, their chamber. Now, inside the chamber, they had a small source that was producing. They had a small source. They had a small. They had a small source, right? And of electrons, right? They were basically going ahead and they had a small source. Now, in front of that small source, they had a gold leaf, a very thin layer of gold leaf, right? So they had a source of alpha particles and they had a very thin gold leaf. Now, the principle of the experiment was quite simple. The source will produce alpha particles. Those alpha particles will hit the gold leaf, and when they will hit the gold leaf, they will scatter. They will travel at a certain distance, right? And we will have a microscope was what they basically used. They used a microscope to actually keep an eye on it. They used a microscope to actually see where the alpha particle was going. This was the setup that they went ahead and they started. I'm so sorry. I think I said the source is for electrons. It was not for electrons. It was for alpha particles. So you had a source. The source was for alpha particles. I don't know why I said electrons. And then you had the gold leaf or the gold foil. Okay. Now, what actually happened? What actually happened in this experiment? What did they notice? What was happening? So, in this experiment, they expected that all of the alpha particles would, pass through the coil. That is what they were expecting at the time. They said, oh, all of the alpha particles are going to, pass through the coil, right? Maybe they will divert a little bit, but that's it. But they noticed quite an interesting fact. What did they notice? They noticed, right? First thing that they noticed was that most of the alpha particle passed through with very little deviation. That was the first thing that they noticed. Most of the alpha particle passed through with very little deviation. Now, how did this help them figure out the structure? How did this help them figure out the structure? So basically, they knew at this point, they already knew that an atom is made of positive and negative charges. They already knew this. This is information we already had, that it's made up of positive charges and negative charges. Now, they saw that this is an alpha particle. An alpha particle, if you remember from your previous years, an alpha particle has has two protons and two neutrons, right? It's the nucleus of helium. So it has a charge of 2 plus. So they noticed that most of the alpha particles simply pass through the gold leaf with very little deviation. So this allowed them to conclude that most of the atom must be an empty space. They concluded based on this that most of the atom must be an empty space, that positive charge cannot be spread throughout the entire atom. That positive charge cannot be spread throughout the entire atom, otherwise they would not simply pass through. But the majority of them were simply passed through, right? So, and so far, this is what they expected. They expected that the atom will simply pass through. This is what they were expecting as well. So they said, okay, fine, this is what we were expecting as well. Now, what happened after that? What happened after that is quite interesting. After that, they started to notice that in certain cases, they were getting very huge deflections. So if we talk about it, let's say that this is my gold leaf. This is my gold particle. Okay. And this is the nucleus in the center. Now, they noticed something quite interesting. One thing that they noticed was that when they took that alpha particle and they made that alpha particle go through, so the first thing I already told you, the first scenario was that the alpha particle passed through with very little deflection. The alpha particle passed through with very little deflection, right? So they concluded that, oh, the alpha particle, the majority of the atom must be an empty space. Now, what happened after that? Then they started to see some quite interesting deflections, and they were not expecting these deflections, right? These deflections were very interesting for them since they were not expecting them to happen. First thing that they noticed was that some of the alpha particles deflected at huge angles, right? So they deflected at huge, they actually deflected, one second, they deflected at huge angles, right? So then they were like, okay, this is interesting. These alpha particles are deflecting and they're deflecting at huge angles, right? A few alpha particles are deflected back and back towards the source huge angle. So they said, why is this happening? This allowed them to conclude, this allowed them to figure out that actually most of the mass of the atom and a large concentration of the charge is in a tiny central nucleus. They said, okay, so we are seeing this huge deflections. So the point where we are seeing this huge deflection, this is the point where our particle must be passing close to a positive charge, right? Why is it that instead of passing straight through, it's suddenly getting deflected, right? So they said, okay, all of that charge must be towards the center. All of that charge must be straight towards the center. That is why when that when it is passing close to the nucleus or it is passing close to the center of the atom, it is getting deflected. So that if it was spread throughout, then you would see deflection generally. You would see them getting deflected everywhere. But they saw that it was getting deflected when it was passing close to the to the to the when it was passing close to the nucleus, right? So that is how they concluded that a lot of the charge must be concentrated towards the center, right? That is why when your charged particle, when your particle is passing close to the nucleus, it's getting deflected. And then we noticed something even more interesting. They also noticed that when you talk about your gold leaf, so in your gold leaf, they also noticed that there were some particles that were actually going all the way back. There were certain particles that were actually deflecting all the way back. So they would come close to the nucleus and then they would go in the opposite direction, right? So this, they saw this. These were the three observations that they made. This was the third observation that they actually made, right? That some alpha particles deflected through a large angle backwards. So this allowed them to conclude that a large concentration of charge, positive charge, is in one place. This is how they actually came up with the concept of a nucleus. Okay, this is how they actually ended up getting with the concept of a nucleus, that they actually saw that some were completely deflecting back. So they said, okay, so the charge must be concentrated right at the center. The charge must be concentrated right at the very center. So these were the three observations they made. The first one was that most of them were passing straight through, so majority of the atom must be empty. Some of them were deflecting backwards. Hence, there must be a lot of repulsion taking place. So all of the charge is concentrated in one point. All of it is located in one point. And some of them were deflecting at huge angles. They were not going backwards, but they were being deflected at huge angles. So that allowed them to conclude that most of the mass of the atom and most of the charge is concentrated in a very small, tiny central nucleus. So this was the experiment that actually allowed us to come up with a simple concept. Making sense so far? No confusion?
No, miss.
Okay. Now this was the discovery that was made. After this discovery, then now so far we knew, so far the information that we had was this, that the atom has a nucleus in the center where all the charge is concentrated. Okay, then they actually believe, right, that so the nucleus has a charge in the center where all a nucleus in the center. Then we actually had evidence that when you're going to talk about your entire scenario, so we actually had evidence that most of the atom is in empty space. Now, so far we had no concept whatsoever about neutrons. The scientist, so Rutherford was the scientist. If you remember, I told you Rutherford was the one who came up with the structure of atom. So Rutherford was the one who came up with the structure. So Rutherford had determined that most of the atom's mass and all the positive charge was held in the small nucleus in the center, and then the electrons were surrounding the atom. He didn't have a concept of shells yet, but he said the electrons are surrounding the nucleus. Now, there was a small problem. The small problem was that when he was measuring the mass of the nucleus, he would get a different number. But when he would look at the number of charged particles, the number of protons in the nucleus, he would get a different number. So it didn't make any sense that there are not enough protons inside the nucleus, but the mass of the nucleus is much, much greater, right? Now, so now you and I know that the reason for that is neutrons, because neutrons do not have a charge, but they do have a mass, right? So at that point, they had no idea about neutrons. So this was a problem that they were having. They said, okay, why is it that the mass of the nucleus is coming much different compared to the number of protons? If we take the mass of protons, that doesn't add up. There's a difference that is coming. Now, in so this happened around 1900s as well. So, okay, you don't need to know the details of this experiment. You don't need to know the details of the gold experiment. That's why I explained that to you in more detail. That you need to know. The gold experiment you need to know properly, right? But I will just give you an overview of how we discovered atoms. So there was a scientist that found that when he took alpha particles and he, threw them, or he shot the alpha particles on beryllium, so beryllium would produce an unknown radiation that they had not talked about before. They had, not studied this radiation before. They hadn't seen this radiation. So they said, okay, what could this unknown radiation be? Now, there was, so what they did was that other scientists as well, they repeated the experiments using other target materials. So instead of beryllium, they used, other materials as well. So they shot alpha particles at different materials, right? Now, what happened was that they thought of it and they figured it out using momentum, right? So he actually thought about conservation of momentum, the conservation of principle of momentum, that the momentum before the particles are colliding has to be equal to momentum after the particles are colliding. So, and conservation of kinetic energy. And based on that, he actually concluded that the radiation that was coming, the unknown radiation, has to be a neutral particle. It does not have a charge. And it has a mass which is slightly greater than that of a proton. This particle was then considered to be the neutron. So Chadwick was a scientist who did it. That was his name. And that's how they discovered that we have neutrons. So then we got the concept of neutrons. And once we got the concept of neutrons, that's when the structure of atom become a lot more clearer, that the nucleus is made up of protons and neutrons. That is also how they explained the fact that the nucleus has a mass greater than the number of protons. Now, when we go ahead and we talk about it, so now we know that the nucleus contains two types of particles, protons and neutrons, right? So protons and neutrons combined, we call them nucleons, by the way. So if you see the term nucleon, do not get confused. They're talking about protons and neutrons all together. So if you take the proton and you add the neutrons to it, you get your nucleon. Now, when we go ahead and we talk about it, the number of protons in a nucleus will determine the element an atom is going to be, right? Number of protons, and this is information we already know quite well, determine the element. If you remember, I had told previously as well that protons are your identification number. Proton number is specific to each element. You cannot change the proton number. If you change the proton number, you change the element in itself. And in the periodic table, the elements are arranged in order of the proton number, right? Proton number is also known as atomic number. So I'm not going into details of all of this because you know all of this quite well. In 1920s, right, they actually came up with the concept of orbitals. Okay, So they came up with the concept of 1s orbital, 2s orbital, 2p orbital, and that's what we actually study. Now, this was stuff that we already knew. We don't have to, stuff that we had already studied. We knew the structure of atom quite well, and now we know the theories about how we discovered the structure of atom. Now, let's actually get into, we have talked about protons, we've talked about neutrons. Let's talk about electrons, right? This is just the basic structure that we're actually going. Now, when we go ahead and we talk about it, so electrons, okay? When we talk about electrons, so if you remember, the um, electrons inside a metal, right? If you remember, we had studied this last year, that if I want electrons to be released from a metal, I need to provide a certain amount of energy, right? Which we had called work function, if you remember from last year. And we had studied it as photoelectric effect, right? We had studied it as photoelectric effect, where the energy from photons was providing energy to electrons so they can escape the surface of the metal. Right? This was photoelectric effect. And we studied that we need to provide a certain amount of energy, a minimum amount of energy, which we said was our work function. Now, another way that I can cause the electrons to be released from the metal. Is this the only way? Is light energy the only way that I can cause the photons to be released from the metal? No. I can also cause, or I can, the electrons can also be released from the metal by heating it up. This process is known as thermionic emission. So when I heat up a metal, and because I am heating up a metal, the electrons are getting released from the surface of the metal. That is known as thermionic emission, right? When you go ahead and talk about it, what's going to happen? Now, once the electrons are going to escape, let's see. If I take those electrons and I put them in an electrical field, what will happen? And electrons have a negative charge on it. If I take those electrons and I put them in an electrical field, they will accelerate. Why? Because they will be acted upon by an electrical force. So they will accelerate, and they will accelerate towards the positive side. Because they're negative, they will move towards the positive side, right? If these electrons are placed in an electrical field, they will accelerate towards the positive side, right? And as they're going to accelerate, they're going to gain kinetic energy, right? They're going to gain kinetic energy. And how much kinetic energy they're going to gain is going to depend upon the potential difference. What potential difference am I applying? Because it depends upon the electrical field, right? Electrical force. So it's going to depend upon my voltage. What is the potential difference? What is the voltage that I'm providing? The greater the voltage I'm providing, the stronger your electrical force, the more they will accelerate, the more you will gain kinetic energy, right? So this gives us an equation, which is kinetic energy is equals to electron, charge on an electron, multiply by your voltage, right? So if I take the charge of an electron and I multiply it by the voltage, by the potential difference, I should be able to calculate the kinetic energy of that particular electron. Now, when we are talking about thermionic emission, you are going to see thermionic emission quite a lot in cathode rays. You might have gone over cathode rays before in previous experiments. In different experiments, you might have studied in IGCSE in your Unit 1, Unit 2, Unit 3. You might have heard about cathode rays. Oh, we wanted to produce a beam of electrons, cathode rays, right? But what actually is it? How does it work? So, it works by the principle of thermionic emission. We can use thermionic emission to, use thermionic emission to produce electrons and then apply electrical field to accelerate them. As a result, a beam of fast moving electrons is produced. Right? We can get a beam of fast moving electrons. And this is how we can shoot electrons or we can shower electrons for our different experiments, right? Now, when we talk about our electrons, so we actually will see something quite interesting. If I take an electron beam, right? If I take an electron beam and I fire it at a crystal, like we have a normal crystal. So I fire it at a crystal. I will see that it will produce a scattering pattern. And that scattering pattern will allow us to figure out the structure of the crystal. This scattering pattern, the scattering pattern we are getting, will tell us about the structure of the crystal, right? So, would allow us to figure out the structure of the crystal. Now, if you remember, we had done this in last year in our topic that electrons can be diffracted. Remember, we had gone over the electron diffraction pattern as well, that an electron beam can be diffracted, right? And the pattern of diffraction is different than what we saw with alpha particles. Alpha particles were giving us a different result, and the diffraction we were getting with electrons, we did that last year, was a different result, right? And we also saw that the diffraction allowed the scientist to figure out that electrons can behave as waves, and that is how we came up with the concept of de Broglie wavelength, right? And if you remember, the de Broglie wavelength that we had gone over was the formula we had done for de Broglie wavelength, or the wavelength of our electrons, was our Planck's constant divided by momentum. That was the formula that we had gone over, right? Or we can further simplify the formula as de Broglie wavelength is equal to Planck's constant divided by mass into velocity, right? So these were the two formulas that we had done in last year as well, and you will be utilizing them this year as well. You'll be using the same formulas for this year's topic as well. Now, when we go ahead and we talk about it, so this is the basic concept that of when we talk about a structure of our atom. Now, let's go into stuff that we do not know. Let's go over stuff that is new for us, and let's actually talk about something that you might most definitely, I think you have not gone over it before ever, and that is, let's go over the concept of accelerators, particle accelerators. Right? You might have heard of them. might have heard of particle accelerators before, but now we will actually study what are particle accelerators. Okay. Now, if I want to investigate the internal structure of protons, or if I want to study the structure of a neutron, I will have to collide the neutrons and the electrons with other particles that are traveling at a very high speed. And it's important that we use a high speed because we want the particles to have a high energy. Because if the energy is low of the particles will simply bounce. That's it. They will bounce up and move away from each other. We want them to scatter. I want my electron to hit the proton and scatter the proton open so I can study what's inside the proton, right? So I want my electrons to have a very high energy. I want it to be so that when the particles will collide, they will actually break and allow me to see the internal structure, right? So when we go ahead and we talk about it, for that, I need my particles to be fast enough. The faster my particles, the more kinetic energy they will possess. And for my particles to be fast enough, I need accelerators, right? Now, we can take charged particles and we can accelerate them by using an electrical field. By using an electrical field, I can accelerate them and I can change their direction by using a magnetic field. Now, let's go over the different types of accelerators that we actually are going to be talking about, right? When we go ahead and we talk about our particle accelerators, so one of the simplest sort of accelerator that we use is a linear accelerator. Okay. A linear accelerator. So one of the simplest ways that I have to produce high energy, to produce energy high enough for the particle collision is to simply accelerate a beam of charged particles along a straight path, right? That's the easiest way. Take your particles and accelerate them in a straight line. You will definitely get enough kinetic energy where you'll be able to study your internal structure, right? Now, there's a problem with this. If you remember, I told you that the kinetic energy depends upon the voltage. When we talk about voltage, right? So that voltage, there's a limit to. I can't increase voltage to an infinite value. I can only increase voltage to a certain value. The maximum voltage that I can get is limited, right? So technically, how can I get my particles to be that fast? How can I make my particles go that fast? How can I accelerate them to such a high value when I have a limitation of how much potential difference I can provide? So to overcome this problem, particles are accelerated in stages. We accelerate, instead of accelerating them in one go, because that would be the simplest thing. One go, right? But we have to do it in stages, right? We keep the potential difference maximum. Now keep this in mind that we are talking about difference, potential difference. Let's, for the sake of assumption and only for the sake of assumption, this is not how it is. Let's say that the maximum potential difference I can do is 5,000 volts to keep it understand. So on one side, I have 0 volts and on the other side, I have 5,000 volts, right? That's how it works. That's how we create a potential difference. One side will be 0, one side will be 5,000. So the particle, as it will go from 0 to 5,000, it will accelerate. Now, when I will take it to the next stage, it will already have a certain kinetic energy. I have applied the same potential difference, 5,000, But since it already has an existing kinetic energy, so even though the potential difference is the same, it will accelerate and it will get faster, right? Now it will have even more kinetic energy than before. Then I again pass it to the same voltage because my maximum voltage, I cannot exceed it. But since again it is already coming with a very high speed, so when I again apply the force, it accelerates once again, right? So think of it this way, that you have a car that is, there's a pushing force that is accelerating it. So I push the car and it starts traveling at a, starts accelerating, its velocity increases. Then it continues to travel a little bit and then we push it again. Now the force I'm applying is the same, but since it already has existing kinetic energy, it already has existing velocity, it will speed up even more, right? So we do it in stages. The maximum velocity, the maximum over a potential difference will be the same, but we accelerate it again and again. So we will repeatedly accelerate at the maximum achievable potential difference. Whatever that potential difference is, I will accelerate it again and again and again. And as a result, we are able to accelerate it enough where it is actually where we can actually go ahead and get them to be fast enough where we can actually use them for studying the structures. If I give you an example, so we have a linear accelerator in the USA. It's 3.2 kilometers long. That's how long it is, the accelerator. It's 3.2 kilometers long. It's in Stanford, USA. It can actually, um, they actually, if I remember correctly, they were providing 50 billion volts of potential difference. The potential difference is around 50 billion volts, right? So that's how much they actually have to use to go ahead and provide you the energy to the electrons to get them to accelerate, right? Now, so we can use this concept for our, that's what we can go ahead and actually use accelerator for. This is one of the most commonest types of, this is how accelerators basically work, right? So we can, so for example, if I want to, and I can do this with different particles. I'm talking about electrons again and again, but I can do this with different particles. I can use alpha particles. I can do it with, we're going to study muons, heptons, leptons. I can do it with any particles whatsoever. So for example, I want to do acceleration with a electron. So I will use an electrostatic machine to produce electrons, and then I will take an electrostatic machine and I will put it inside the accelerator. Once the electrons are produced, they will move in a straight line. Okay, they will move in a straight line. So they are going to move in a straight line, and we are using alternating voltage, right? So what is going to happen, since we're using alternative voltage, so the alternating voltage is made to change in such a way that when the electrons reach the middle of the tube, so okay, to discuss this, let me draw a structure for you to make it a bit easier. These are the multiple tubes, okay? I'm doing the experiment in multiple tubes. Because if you remember, I told you that we actually, when we do the experiment, what do? We use multiple tubes for our experiment, right? If you remember, that's what we had gone over, that we have to do it in stages. So I will be doing my experiment in stages. So what am I going to end up seeing? I'm going to, let's say that this is my, over here, uh, this is my tube A, this is my tube B, this is my tube C, this is my tube D, and then, okay, let's make a tube E as well. Now, what is going to happen over here, somewhere over here, I'm going to have my, not inside the tube, but somewhere outside the tube, I'm going to have my, I'm going to go ahead and I'm going to have my, I'm going to have my generator, right? The generator that is making the electrons, okay? So I'm going to have my electron generator somewhere over here. And this electron generator is now producing our electrons. So what are we going to go ahead and actually see? We are going to see, what are we going to do is that I'm going to go ahead and connect all of this setup to a alternating current. So I'm going to take my A. Now, I have taken all of this and I have connected it to an alternating current. Okay. Now, what is going to happen? That I used my electrostatic machine, the one machine over here, and I used it to produce my electrons. These electrons, once they have entered this tube A, so they will start to move in a straight line. Now, what's going to happen that I have connected all of these tubes to alternating supply. Okay. So I will change the alternating voltage in such a way that when the electrons reach the middle of tube A, it will become negative. Now what's going to happen? Since the tube A will become negative, the electrons will be repelled away from tube A and they will enter into tube B. When they are into tube B, again, I will turn tube B negative. So tube B, the electrons will again, they already were at a higher velocity than before. Again, they will accelerate and they will go to tube C because of repulsion. Now that they're in tube C, again, now they're even faster than before because we accelerated them. Again, I will turn tube C negative. Tube C will become negative. Again, the electrons will repel away. They will experience electrical force. And again, they are going to accelerate even more. So this is going to keep on happening until they end up reaching the target, whatever the target is, right? So we are, so now the thing is that in order to keep accelerating particles, in order to make sure the particles are moving faster and faster, the tubes must be longer and longer, okay? Don't go on the diagram I made, it's not correct. The tubes will be longer and longer. A will be the shortest, then B, then C, then D, right? To make the particles go faster and faster, the tube will have to get longer. Okay? So A will be the shortest, then B, then C, then D, then E, so on and so forth. Right? So what's going to happen? So they will actually continue to travel at a higher and higher and higher speed. Right? Now, this entire structure has to be in vacuum because we cannot afford to have air particles. If air particles are going to be present inside my accelerator, this is going to be colliding with my air particles. I cannot have my electrons collide with the air particles. So it has to be done in a vacuum. And also, this type of an accelerator, the limitation to this is how long you can afford to build it. How much time can I spend building an accelerator? The longer I make it, the huger I make it, the bigger my accelerator is going to be. The bigger my accelerator is going to be, the more I can do with it, right? But it's limited by how much time I can actually spend doing it. So this is how an accelerator works. And we use these accelerators to actually perform collisions. So we are going to be taking a look in this topic at I told you fundamental particles, right? So we're going to be taking a look at fundamental particles. So in fundamental particles, you will see that by using these large accelerators and by using colliders, right? Accelerators and we have colliders, right? So using them, we can actually shoot particles at protons and neutrons, and we can break them down and we can discover other type of particles. That's how we discovered a lot of other type of particles that we have not gone by before, that we have not gone over before. Now, when we go ahead and we talk about it, okay. Then is everything, by the way, making sense so far? I hope there is no confusion in what we're talking about.
No, miss.
Okay, then I think we will go ahead and stop it over here for today. We have to actually, the next topic is slightly longer and I don't want to start it and then leave it in the middle. So we'll go ahead, okay, we'll go ahead and stop it over here for today. And inshallah, in the next class, we'll go ahead and we will continue with the topic. All right?
Okay, miss.
Okay, thank you so much, Radhana. I'll see you in the next class. Have a good day.
Thank you, miss. Bye. Take
Allah
care.
Hafiz. Bye.
Allah Hafiz.